Today we will be discussing deflection of beam, right. So, it is deflection of beams. That is the general topic of today's discussion. In our previous class, we are talking about stresses, and we have tried to get the idea that stress is a very important quantity. All the time we have to determine, calculate stress to have some idea regarding the structural safety, because that stress should be within certain limit, and that limit we have defined as allowable stress. Now, deflection is not that important like stress, but there are some situations where we may require to get the information about deflection. In that case, the knowledge of calculating deflection at some point is necessary. So, that is one aspect. Apart from that, there is another requirement which I should say it is much more important. In that context, I can explain in that manner. Say a structure, we divide the type of structure into two categories. One is called statically determinate problem, another type of problem we say statically indeterminate problem. So, if we say a structure in general, structure, so one type is statically determinate type, another is indeterminate type. Now, what is statically determinate type and statically indeterminate type? Last class we are talking about equation of statics, right, and we have seen there are three equations if we handle a two-dimensional problem or plane problem. Summation of all the forces along x direction we have taken 0, summation of all the forces along y direction equal to 0, plus we can take moment at any point of all the forces, it will be equal to 0. So, these are basically equation of statics if we think in terms of plane problem. Now, there are some structural problem where the unknowns, which are basically the reactions which are getting from the supports, those quantities we can determine with the help of equation of statics. So, it can be determined by the equation of statics. So, it is statically determinate. Already you have taken a problem, two supports, one is hinge, another is roller, we got three unknown reactions, and there are three equations we have applied, we obtained the support reactions. So, that problem was absolutely a statically determinate problem. Now, all the structures will not be statically determinate. Say there might be more supports, maybe both the supports hinge. So, you will get 4 reactions, you may get 5 reactions, you may get more number of reactions. Now, not necessarily you can't force that support should be such the reaction number will be always within this number 3 depending on the practical situation, it may be any number. So, it cannot be solved by only the equation of statics. So, that category of problem we say statically indeterminate problem. So, it cannot be determined with the equation of statics. So, that is why we say it is statically indeterminate problems. Now, the question is how we will solve a statically indeterminate problem, but real structure may be statically indeterminate. It can be solved. So, we will require more number of equations. So, we have 3 equation of statics. So far the problem is within a plane, say our unknowns are 5. So, we will require another 2 equations, and those 2 additional equations it will come from the information regarding the deformation of the structure. So, structural deformation is nothing but the deflection of the structure. So, deflection of structure we will try to utilize to get some more information that mode information will be reflected in the form of mode equations. So, structural deformation or structural deflection, those relationship will be utilized in the form of additional equation in addition with the equation of statics, and that will help to solve the entire problem. So, ultimately what will be our problem? Our problem will be, if we are interested only bending moment, shear force or stresses, and problem is not determinate, we have to go for some calculation of deflection of the structure, because that will help to give some equation. So, that is, I think, one of the major requirement for having some understanding regarding the deformation of a beam or the deformation of any structure. So, we can start with a beam, because it is one of the very elementary structural element. So, that concept can be extended to some other complex type of structure, like as a frame problem or other type of structural problem. So, here our starting point is deflection of the beam, and we will start with statically determinate problem. Everything will be known, at least the forces, reactions. So, how to find out deflection, that part we will study. Okay. Once that understanding will be developed, with that we can go ahead for a statically indeterminate type of problem for finding out the unknowns, so that we can determine internal forces, internal moments. Simultaneously, we can find out the deflection of the structures also. So, it will be an integrated process, deformation calculation, stress calculation, both will be carried out simultaneously. Now, if we try to find out the deflection of beam, there are many methods available we can use, but here my attention is to cover only very basic type of methods. At least I will try to cover 2, 3, maximum 4 types of method. There is no point of covering all the type of methods available in the market. What are very basic type, very fundamental type, which can be used without much problem, we can go ahead with that. Now, I will start with a method, it is called differential equation technique, or so this is defined in a different manner. Sometimes it is defined differential equation method, differential equation technique, or integration of differential equation, integration of differential equation technique. So, basically it is dealing with some differential equation of the beam problem. Here when we will be handling with differential equation, we have to start from the deformation of the beam with some bending moment, with shear force, with load, and all those quantities. So, before coming to that exact treatment what is done in this particular method, let us try to find out the relationship between the different quantities. The different quantities, just now I have mentioned, one is the load, shear force, bending moment, slope, deflection. So, they are not separate quantities, they are closely associated with each other, and some dependencies are there in between. So, let us try to get the idea how they are related. We can take a beam like this, you can take any beam. There might be some loading here. So, it is just I have drawn a simply supported beam, means beam one end is hinge support, another is a roller support, and combination of that it will give a stable structure, determinate structure, and some loading. Here hinge will provide 2 reactions, roller will provide 1 reaction. So, 3 reactions it can be determined with the equation of statics. Now, if we try to make the hinge as a roller, the left support, what will happen? Number of unknown will be less, 2, your equation will be more. In that case, structure will not be stable. So, all the time we can't make it as minimum as possible. So, a minimum number of restraint is also necessary, because any structure basically we want to fix in space. So, it will require some support. So, at least 3 direction it should be restrained. It should not move this way, that way, it should not be stable but rotate. So, all the possible movements we have to restrain. So, these are the minimum thing, and if we go beyond minimum, then it will be statically indeterminate. Now, here I have drawn a line to represent the beam. So, basically a beam has a very small dimension along the depth and width compared to the length. So, length is the predominant dimension, and normally all the breadth and depth quantity we more or less represent in a compact form. We take I value. So, everything is incorporated there for representing the bending. So, the variable here is only along x, and this line is basically the neutral axis or neutral line of the beam. Now, under the load it will undergo some bending. So, we are trying to plot the deformation of the beam with this neutral axis. We sometimes we say it is elastic line, right, because whole thing is elastic analysis, and it is a line, we say it is elastic line. Now, it will undergo some deformation in an arbitrary manner depending of the type of load. Now, if I put here some axis system, say x along the axis of the member, and y is perpendicular to that. So, we can say the deformation of the beam or deflection of the beam, it can be represented as, say, y equal to function of x. So, y at any point, say at a distance x. So, this is x, that will be the y. Okay. Now, it is different x, it will be different y, and it is another x, it will be another y. So, x is a variable quantity, depending on x you will get the value of y. So, y is a function of x. Now, what is y? Y is the deflection, right. Now, if I take the derivative, say y dash, it is nothing but your dy by dx or f dash x. If we have the expression of the function, we can take derivative. So, it will give the slope of the line, right, slope of the elastic curve, that we say it is, sometimes we write as theta. Theta is the slope of the elastic curve. Now, the y is the deflection, its derivative is theta. Now, if we take further derivative, we will get d2y dx square or y double dash x or f double dash x. That quantity will have some relationship with moment, right. So, if we take y double dash or this one, this quantity will be equal to m by ei. So, first slope in first derivative, second derivative is this term is basically the curvature, and that curvature will be equal to the bending moment divided by ei. Ei term already we have defined, it is basically the flexural rigidity of the beam. So, m is the moment, and that expression is very important. Sometimes we write as minus ei d2y dx square equal to m. So, that equation in a different fashion we have written. So, this part d2y by dx square, this part is called basically curvature. It is basically curvature. So, curvature is inverse of radius of curvature. The curve will have some radius of curvature. So, inverse of that will be curvature. So, if we take a straight line, radius of curvature will be infinite and curvature will be 0. So, straight line no curvature, but if we have some curvature, so we will have some finite value of radius of curvature, right. So, this d2y by dx square will be the curvature, and m is the bending moment, a is the flexural rigidity, and that relationship is called moment curvature relationship. This is right. Now, just now I have mentioned d2y by dx square is curvature, curvature of the deformed shape of the beam or the elastic line. So, if we say it is a deformed shape of the beam, now anywhere if that is the radius r, so d2y by dx square it will be 1 by d2y by dx square, right. So, that this is the radius of curvature and this is d2y by dx square is curvature. So, the reverse term of that is your radius of curvature. In that context, I should say the expression of radius of curvature and curvature is not exactly the same. For a very arbitrary curve, say any arbitrary curve, the r, if we try to represent, so r is basically your d2y dx square divided by 1 plus dy dx. So, that is the general expression for that will be 1 by r. So, 1 by r is the curvature, it is d2y by dx square 1 plus dy dx whole square whole to the power 3 by 2 or 1.5 whatever you can say. But here the denominator part we are not taking. The reason is very simple, because we will be dealing with structural problem, and structural problem deformation will not be very large, it will be very small deformations, and when deformation is small, its rate of change is basically slope, dy by dx slope will be much more small, and square of that it will be much more small. So, this quantity will be practically going to be 0, we can neglect that. So, this part if we draw, it will be 1 to the power 3 by 2, it will be basically your 1. So, approximately we can write 1 by r is your d2y dx square for small deformation problem. In our case, it will be a small deformation problem. So, we can simply write 1 by r equal to d2y by dx square, and this d2y by dx square, they are related to basically bending moment with a factor ei, and some minus sign will come. Here I want to tell you, we can compare that equation with your normal stress strain relationship. Say a normal stress strain relationship is, say here I am writing in the side sigma equal to your E into epsilon. Now, sigma you can compare with m, and strain you can compare with your curvature, and E you can compare with ei, right. So, it is basically something similar or analogous to your stress strain relationship. So, it is not stress, it is moment. Moment is nothing but one of the stress resultant, because throughout the depth of the beam, your bending stress will vary. It will be maximum 0, minimum. So, total effect if you take, that is basically the bending moment. So, M is the resultant of the stresses. So, it is stress, one of the stress resultant. So, that stress resultant we can compare with stress, and here strain we can compare with the curvature, and E here something related to EI. Now, we have written minus. Why we are writing minus here? I think it is basically a matter of sign convention. Sometimes we write here, say d2y dx square EI, we say somewhere you will find the relation is something like this. So, you can take plus, you can take minus. Where will take plus, where will take minus, that will depend absolutely on the sign convention. Say I am taking a axis system, whatever we have taken earlier. So, it is x, it is y, right. Now, there might be a bending phenomena like this, there might be a bending phenomena like that. So, earlier we are trying to define as sagging, hogging type. Okay. Now, here there will be a type of moment, and here there will be a type of moment. Now, x y d2y by dx square is what? Your d2y dx square, we can say it is dy dx of dy by dx, and dy by dx is what? It is basically theta. So, we can write it is d theta by dx. Now, what is theta? Theta is basically, if we draw a line here, that will be the theta. So, it should be theta, and theta will be positive when the way we have written or drawn, it is basically theta. If we increase x, your y value is increasing, but if we draw like this, with the increase of x, y is decreasing, right. Why it is going towards the negative side. So, that will be a negative slope, that will be a positive slope. Okay. Now, if I take that type of problem, here slope will be positive and here slope will be negative. So, d2y by dx square is rate of change of slope. So, it will be, it is changing from your positive slope to negative slope. So, curvature will be in that case negative, because here slope is positive, here slope is negative. So, whatever negative value minus that positive quantity will be negative divided by dx. So, here curvature is a negative curvature, but here this is a negative curvature, negative slope, and that is a positive slope. So, positive slope means with increase of x, the value is increasing in the positive direction of y, and here if you increase x, y part is decreasing. Okay. So, this is a negative slope, that is a positive slope. So, rate of change of slope, this minus this divided by length dx, that will be basically d theta by dx or d2 by dx square. So, this will be a positive curvature. So, this should be a positive curvature, and this should be a negative curvature, right. Because if it is a sagging one, in terms of xy system, your curvature is becoming negative, d2y dx square is becoming negative, because slope we have defined, which is plus and minus, and change of rate of change of slope, that is basically d2y by dx square, that is becoming negative here, this is becoming positive here for the case of hogging. Now, it is a matter of sign convention. If we take sagging moment is positive, then here our this side sign will be minus. if we take as hogging is positive, we will take the sign of m will be plus. So, it is again a sign convention. So, normally last day we are trying to take sagging as positive, we can go ahead with that sagging as positive. So, here at that level we will write moment with a minus sign. So, we have started y, its first derivative is slope, second derivative with ei will be minus moment. Now, next part is your dm by dx. If you take the derivative of a moment, you will get shear force, or if we put here it will be minus ei d3y dx cube. So, shear force is what? Derivative of moment. What is moment? Moment is your minus ei d2y by dx square. So, for the derivative of that and minus sign we have to incorporate. Okay. And the last term is the loading q is equal to minus dv by dx, or minus it will be plus, it will be ei d4y dx to the power 4. Right. So, what is q? Q is basically the intensity of the load acting on the member. Member is here a beam problem, it is a beam member. Okay. So, we are putting a load, we are getting a displacement. In between your slope is there, moment is there, shear is there, and they are related like this. So, if we know the equation of the deflected curve, if we take the first derivative, we will get slope. Second derivative multiplied by minus ei, you will get moment. Another derivative, you will get shear force. Another derivative, you will get how much is the intensity of the load. Okay. Right. So, all the four quantities, deflection, slope, moment, shear and load, rather 5 quantities, they are related like this. Okay. Okay. Now, sometimes we use some of the equations for finding some of the important quantities, say moment and shear force. Relationship is just one order derivative difference. Say we want to get the maximum bending moment within a particular region, we have the equation, and equation is not very symmetric type. So, from the physical look you can get the idea it will be at the center, it may be somewhere intermediate, but you have to determine what will be the maximum value and where it will be located. You can find out the value of moment, because if you substitute x equal to how much from the equation you can get it, but you require the information where will be the location, means what will be the value of x. So, in that case that will be very useful, where moment will be maximum. So, shear force should be 0, right. So, any maximum or minimum quantity its so it will go to a peak and come to the lower side, means their slope, means derivative will be equal to 0. So, shear force equation, if we equate 0, you will get the location, the value of x, at what x value shear force is becoming 0, corresponding to that value your bending moment will be maximum. So, that x value you can substitute in the expression of bending moment and get the maximum value of the bending moment there. Okay. So, these information sometimes we will be using for finding out some specific problem. So, these are very very important relationship, deflection, slope, bending moment, shear force and the load distribution. Okay. So, they are related with that. Now, in connection with our primary theme of today's discussion is deflection of beam. The first line on this page, that is moment curvature relation ei d2y dx square equal to plus or minus m. With that we will try to solve deflection of beam using differential equation technique, because this is the differential equation, and that differential equation we will utilize for finding out the deflection of the beam. Now, we shall take some simple cases and try to explain how the method works. I can take a cantilever beam problem, which is quite simple type of problem. Say load is acting at the free end, so it is P, and it has some length, some E value, some I value. So, this is a beam, left support is fixed or clamped, right side is free, at the free end there is a vertical load P, the total length of the beam is L, it has a material property E, cross sectional property is I means its second moment of area or moment of inertia of the cross section. It is a uniform cross section, everywhere it is EI. Now, under the load, the deformation will take place like this. At this support there will be no deflection, there will be no slope. So, it will go gradually, it will deform. At the tip there will be maximum deflection, maximum slope. I know. Here if we take some axis system like this x and it is y, we can start with our differential equation. Differential equation is nothing but your moment curvature relationship. So, we can write EI d2y dx square equal to minus m. If we say sagging is positive, it will be minus m. Now, what will be the expression of m? So, m part, m is bending moment at any cross section. Say this is x y. So, if we take any value of x, what will be the moment? If it is x, this part will be total length is L minus x. So, P into L minus x, and P L minus x will be your hogging moment, and sagging moment will be minus of that. So, it will be P L minus x minus, if sagging is considered to be positive. Say here any station. So, P is the force and distance is L minus x. So, P L minus x, what will be the type of moment? The moment will be in that direction, right. So, that moment will generate stress, tensile stress at the top. So, it is something like this. So, hogging moment, tensile stress will develop at the top. So, if we take sagging as positive, we have to get a moment. So, the moment we are getting, it is basically negative moment. So, it is minus is, it is not sagging, it is hogging, and the value will be P L minus x. Now, here if I substitute that value, this will be equal to E I d2y dx square, this minus it will be plus L minus x. We could take hogging as positive. In that case, we could write this is plus, and this we could write plus. If hogging is positive, this should be plus, and here also it should be, it is basically sagging hogging moment. So, it will be plus, and if we take sagging also, in both the case it is negative. In any case, if you start sagging as positive or hogging as positive, this equation will be automatically coming to be the same equation. Okay. Right. Now, this is our differential equation. So, E I d2y by dx square equal to P L minus x. So, this equation we have to integrate. So, if you integrate, this is a very straightforward equation. It will be dy by dx, and it will be P L minus x whole square divided by 2, and there will be a minus sign this side, because with x there is a minus quantity, plus there will be some constant, say C1. Now, next step we can take a further derivative, it will be EI y, it will be minus P L minus x. So, 2 will be now 3 and below 3 will come. So, 3 into 2 it will be 6, and from x another minus will come, and this minus and minus will be plus, and here it will be C1 x plus another constant, you will get say C2. Okay. So, integration of the differential equation already obtained. In first integration we got first derivative from second derivative, in the second level we got without derivative direct y we got. So, the last line is the expression for y deflection, previous line is the slope, previous to previous it is basically the curvature relationship. Okay. Now, in that process we got one C1 and C2, these are the constants, and these constants are unknown here, these constants we have to determine in terms of say L, E, P something, whatever information we have related to the structure. So, here it is a beam problem. So, E, I, L, P, these are the quantities. So, in terms of those we have to determine, and those quantities can be determined using the boundary conditions. So, at the two ends there are some conditions, and those conditions will be utilized, those are we say it is boundary condition. Say here this is a fixed support. So, y or the deflection is 0 plus this point itself slope is equal to 0. Not necessarily it will be all the time at the same point. If we have a simply supported beam, deflection will be 0 here, deflection will be 0 here. Okay. Now, we have to get C1 and C2 from your boundary conditions. Okay. So, BC is boundary conditions, right. Now, we have the equation, let us put the condition. So, first of all at this level we put say at x equal to 0 your d2y by dx equal to 0, and the second level we will put at x equal to 0 y is equal to 0. So, first we will get C1 value you can substitute here, in the second level once you will put that requirement for deflection is equal to 0 we will get C2, right. Now, if I take at x equal to 0 theta equal to dy dx 0, so that condition will give your EI into it will be 0 because dy dx 0 minus P L minus 0 square divided by 2 plus C1. Okay. So, left part will be entirely 0 and C1 we can write in terms of minus P L square divided by 2. Once C1 is determined, we will take the last equation. So, at x equal to 0, your y equal to 0. So, that condition will give your EI into 0, that will be equal to your P L minus 0 Q divided by 6 plus C1 part you can substitute, or you can keep it C1 multiplied by x, x will be equal to 0 plus C2. So, these two terms are now 0. So, C2 will be minus P LQ divided by 6. C1 will be
negative.
C1 will be positive because this is a minus sign, it will be plus.
C2 will be negative.
Right. C2 will be negative, right. Now, on C1 and C2 we have, we can write the expression of slope, we can write the expression of deflection. Say if we write the expression of slope, it will be theta equal to dy by dx, that will be equal to 1 by ei minus p L minus x square divided by 2 plus C1 just now we have determined, it is P L square divided by 2, right. So, in last page we have made minus P L minus x square divided by 2 plus C1 is P L square by 2, ei part we have put right side with a 1 by form. So, that will be the expression of that. Anyway, this equation can be rearranged, because if you break P L square by 2, that part will cancel. So, you can put it like this or in a different form. Okay. So, in different book you may get expression in a different manner, but ultimately it will be the basic terms, it can be generated from there. Okay. Now, if we want to find the maximum slope will occur at the free end. So, we can get theta max will be 1 by ei, we can put x is equal to L. So, this part will become 0 and that will be P L square divided by 2, or we can say P L square divided by 2 ei, and this will be at x equal to L, right. So, at the free end we will get the theta will be maximum, and that value will be P into L square divided by 2 ei. Okay. So, this term is becoming 0. Okay. Say x.
X is equal to L. But we are calculating theta at x.
Theta at x equal to L.
But when x is L, that is
End slope, maximum slope. That will be P L square by 2 ei. Now, this is one quantity P L square by 2 ei, that is a cantilever subjected to a load at the free end, we are getting the maximum slope there, P L square by 2 ei. This is one of the very important terms. There are some very standard cases. This is one of the standard cases, and the value is one of the standard quantity. So, if we try to solve a relatively difficult problem, some of the quantities like this P L square by 2 ei, that type of quantity will derive some of the quantities here. Okay. Those quantities it will be utilized later on. Say a beam subjected to fully uniformly distributed load, what will be the maximum moment at the center? Omega L square by 8, and that part frequently we use. Okay. We need not take a piece of paper, try to derive what will be the maximum. So, it is just instantaneously we say it is omega L square by 8. So, if we try to evaluate deformation of a structure, deflection of beam, some of the quantities at least we have to keep into our mind, otherwise all the time we have to keep a book and take the help of that. What is the value of maximum slope here, maximum deflection here. Okay. Now, in that process I am trying to find out some standard relationship plus the procedure I have explained. By that time I think you got the feeling. So, the starting point is the differential equation, and differential equation is nothing but your moment curvature relationship, that is ei d2i dx square equal to m, and m that will be the expression of the bending moment diagram, expression of the bending moment at any arbitrary section. Okay. So, it is a function of x. Once you get that expression, you have to integrate twice, you will get two constants, and these two constants you have determined with the help of boundary condition. So, slope 0, deflection 0, some information you will have for a particular structure. Now, a slope expression already we have obtained and the maximum slope. So, next step should be the deflection. C1, C2 we can put in the equation of your expression of y, it will give the equation of the deflection of the beam, and we can find out the maximum value. Normally that will occur at the same point, the free end of the beam. So, let us come to that part. So, it will be y equal to 1 by ei, and here we got p l minus x q divided by 6 plus C1 we got p l square divided by 2 into x, and C2 we got p LQ divided by 6. So, we have just substituted C1 and C2 in the expression of y. Their EI part was in the left side, that part we have put on the right side in the 1 by form. So, that will be the expression. This can be arranged in a different form in a way you like. It may be given in different form in different places. Okay. But if we are interested for finding out the maximum value of y, so at x equal to L, y equal to y max. So, y max it will be 1 by ei. The first term will be equal to 0, because x will be L, L minus L, it will be 0. So, there it will be p L q divided by 2 minus p L q divided by 6. So, it is basically both are p L q. So, it is a half minus 1 by 6. So, half 1 by 6. So, if I just make a small calculation, so it will be 6 means 3 minus 1. So, it will be 2 by 6, or we can say 1/3. So, we can write phi LQ divided by 3 EI, that will be the y max. So, this is another important expression. So, we got the expression for the elastic line. So, that is the line, that is the expression for that elastic line, and maximum value we got P LQ by 3 EI. Sometimes we get confused whether it is L square or LQ L4. That form is there all the time. You will find EI below, here P L, the unit you can always check. Okay. So, EI means E will be in SI unit Newton per meter square, and I will be meter to the power 4. So, below it will be Newton meter square. So, here P will be Newton, it will cancel. So, Newton meter square means it will be LQ. So, meter cube by meter square, it will be meter. Say slope you got PL square. So, it should be a dimensionless quantity, there should be no unit there. Okay. So, we can apply those ideas to check the order of L, LQ or L square or L4 if you are little bit confused, try to recall from your memory. So, it is basically a simple cantilever beam problem. We have tried to find out the deflection using differential equation technique and try to get some maximum values of bending moment and shear force. Right. Now, up to this we can keep in this class. In the next class, we will go ahead with similar type of problem and try to find out some standard relationships. All right. So, we shall continue whatever we have trying to cover in the last class, that is deflection of beam, and we are trying to solve the problem with differential equation technique. We have taken a simple beam problem. It was a cantilever with some point load at the end. With that, I have tried to explain you how to find out the final equations, how to find out the constants through boundary conditions, and from there we tried to obtain some standard values of maximum deflection, maximum slope at one of the end. Now, we will try some other standard cases and try to get some important relationship. Technique is same, problem will be little different. Now, I can take again cantilever problem with a little different type of load. So, structure is same, it has a length L, E, I, support identical, it is fixed, that is free, only the loading is different. The idea is to handle a different type of load also, I think, before changing the type of structure. Next step we can change the type of structure. So, our first job is we have to find out the expression for the bending moment. Right. Now, at any distance x, so there is one cross section, what will be the expression of bending moment? We can calculate from the right end because that is a free end, it is easier to calculate. So, beyond that section right side, the loading is, first of all the length of that will be L minus x, and the loading is say W or omega, that is intensity of the distributed load, the load per unit length. So, length is L minus x and W is per unit length, that is the load. So, total load will be W into L minus x, and that is in a distributed manner. So, moment will be one of the quantity, that is another important quantity. Right. So, same problem with a distributed load, we have tried to repeat that process with a different moment expression and got the values theta max, y max. Now, I will take a problem where your type of structure will be different. So, beam will not be cantilever beam, say we will take a simply supported beam. So, two supports at the two end and take some load, say we can take uniformly distributed load, whatever we have taken, at least load will be same like this, but support condition will be different. So, this is a distributed load of intensity omega or W, and the member is some EI is the flexural rigidity. This is the length, this is x, this is y. So, our first job is to determine the expression of bending moment. Now, if we start from this end or the other end, both the side supports are there. So, we have to know the value of those reactions. Earlier case, support was on the left side and one free end was there. We were trying to proceed from the free end. We need not bother how much will be the reaction at the supports. But here we can start from this end or other end, both end are supported. Okay. So, first job is you have to find out the reaction, and that will be utilized for finding out the bending moment expression, and that will go to the differential equation. Now, here there will be one reaction, and here so this part you can say y, and this part we can say r y, it is say r x, at say a, at a, this is b, say left end if we say a, right end if we say b, it is r along x at a, r y, y at a.